Ja estem? Vale. Bueno, moltes gràcies per venir. Avui tinc el plaer de presentar-vos a la Maria de la Fuente. La Maria va estudiar Geologia a la UAB i després va fer el màster a la UPC. La tesi la va fer a Southampton amb l'Héctor Moreno, que potser els de Geologia el coneixeu, i el postdoc l'està fent a la Universitat Lliure de Brussel·les. Com que té molt de temps lliure, es dedica també a fer d'ambaixadora de pacte climàtic al Parlament Europeu. Això és una cosa que va organitzar la comissió, no? I bueno, avui ens parlarà sobre el metà i una visió, em sembla que una mica multidisciplinària, de biologia i geologia. I bueno, us deixo amb la Maria.
Gràcies, Xavi, i gràcies a tothom per venir. I think the talk is going to be in English, so I'm just going to stick to it. But I'm happy to answer any questions, Spanish, Catalan, French, as much as I can. So this is what we are going to be talking about. So since we've come from an oceanographic campaign in the Antarctica, I just want to make, the parallelism with diving into the topic that I'm studying at the moment. And more particularly, we are going to dive into what we call the benthic methane biofilter. So here we are going to be talking a lot about, yes or not? About methane, but not only methane as CH4 as we know it, and where this carbon that constitutes methane goes when we are talking about marine environments. So this work, it's part of my postdoc at ULB, but it's also in collaboration with the University of Southampton through Héctor Moreno and Tim Minshall, and the UPC here in Barcelona together with Jean Baunat. So Xavi already did this job, but I always like to introduce myself because I am someone who likes to wear different hats at different moments. So you can see me either, doing some sampling on boats, laboratory stuff. I mostly do coding, but this is other things I like doing. Also like speaking at the parliament or just like doing some science communication. Essentially, I'm a geologist. I also did a master in geotechnical engineer. I hold a PhD on earth and ocean science, and that's the first time I was in contact with methane hydrates that I will explain in a few minutes. And I had the amazing experience to be involved in oceanographic campaigns, and that's why I'm also familiar with some of the laboratory parts of these campaigns. And at the moment, I'm working on modeling-based research of methane. But for me, the perfect scientific combo comes when you actually put together the numerical modeling, but also with the broad idea of the scientific question, together with this transversal way of seeing science. It's not just science per se and science that needs to stay within academia, but like the science that you can bring out and use as a tool for society. And linked to this, I'm very keen into breaking barriers when it comes to science communication, especially because my native language is Catalan and Spanish, so I feel like it's very limited when science is only done in English, so I'm happy to translate all this knowledge into other language so that it can reach other people. I advocate for local and global change when it comes to climate change, which is strictly related to my topic through my ambassadorship at the EU Climate Pact. And I also support women in science, technology, engineering, and maths. So if any of the women in this room are willing to help or they want to be involved, it's the program STEM Talent Girl is a free program in Spain where women are supported by women in science, either to show where you work or what you do, to accompany them on the development of their thesis. And it's a very well program designated here in Spain that can help a lot women to make a difference in the STEM world. And diving into what we are going to see today, I just prepared what it's like an overview of the talk. So when I explain things, you will remember that we went through this very schematically at the beginning. What I want you to have in your head is an image of a cross-section of the ocean especially at the interface between the sediment and the water column. Because if we do this cross-section, we can see here that at some point at a given depth in the sediment, we might have what we call methane hydrates. And here there's going to be a lot of biogeochemical reactions that are going to be important to know what happened to this methane. So first of all, we are going to be exploring if actually changing some of the thermodynamic parameters, we are able to connect somehow methane hydrate stability to climate-driven factors, and if actually this methane has anything to do with potential positive climate feedback mechanisms. Because, as we know, this methane might go out. This is something, and I don't want to do a spoil, but like hopefully the Ice Flame project will talk more about this. It actually seeps out into the sediment, so it's important to see how these two environments are connected. And then we also want to talk about which are the ways or the processes that are capable of stopping this methane from coming out. We have in the room some people working in microbiology. So here we have a consortia that actually feeds, it's like a bit of like a buffet. They use this methane to gain some energy for their metabolic development, and they might be a good sink for methane, but we are going to be exploring this sink more into detail. We are going to see how actually the efficiency of this sink it's being defined, and what does that mean in terms of like how much methane can go out into the water column. We are going to look at fluid flow regimes, but also some bioenergetic limitations. And then we are going to see how this efficiency is actually linked to how much carbon, not only in the form of methane, but any form of carbon can be injected into the ocean. My part, it's the most boring one, I guess, in the equation, which is the modeling part. So I'm going to go really not into detail, like very general view of what the model is doing. But obviously, if someone has some questions, I will leave the workflow of the model in the screen so you guys can ask. And I'm just going to leave the room with some take-home messages in case someone wants to take some notes at the end of it. So my first question is anyone familiar with methane hydrates in the room? Yes? No, it's also a good answer. Like this, I can explain what they are. So methane hydrates are these white-ish materials that we can see here. So this is kind of like a sandy sediment from the Gulf of Mexico, in which we see these parts here. Usually when I ask, people say it's ice or it's salt. It looks like both. It's actually a crystalline structure in which, to a bare eye, you wouldn't say there's nothing else there. But I promise you there's like something much more going on here. If you see there's like a bit of like gas around the sample, this is because in order to see these at the room conditions, we need to extract them from a place where they have been preserved at a very low temperature. And that's why we have the liquid nitrogen surrounding the sample. Actually, what's inside here, it's methane. It can be many other gases, but when we talk about methane hydrates, what we expect to have within this frozen water structure is methane, but it can be any other gas molecules. And what we see here is that within the cage of water molecules, when they are frozen, when they are solid, we have some gas molecules being trapped inside. So if you froze some water in your freezer, you have the same structure, but only these cages are going to be empty. If the environment where this water is being frozen contains enough water and enough methane at a given temperature and pressure, you might trap, at a very compressed volume, this gas inside. And it's not just me saying this. I can actually prove there's some gas inside, which is interesting. So here we have a lake in Alberta, Canada, and what they're doing here is to break this kind of like bubble of ice, and they're exposing the ice to a flammable source. And what's happening here is that actually we have a bubble of methane, just the gas, that it's coming up. So there's a lot of methane being produced in the bottom of lakes, for instance, here because of methanogenesis. So the microbes and all these consortia, it's eating the organic matter, and they're generating methane as a byproduct to obtain their energy. This methane is accumulating. It exceeds the saturation of the sediment, it generates a gas, so there's a next solution. This gas, it's accumulating in the form of a bubble, it rises up into the water column, and it reaches the surface where it's very, very cold. So the hydrate, it's actually capable to form around the bubble, and this is a coating of gas hydrate. And then what they're doing here is actually to break this hydrate coating, exposing the gas that is inside to a flammable source in order to verify that actually this is not just ice, but ice containing gas inside. And actually, if we expose the first sample to the same process, because we are in atmospheric conditions, the same will happen to this sediment. And actually, you end up having almost nothing of what we saw before. And why is this important? Well, it's important because if you like a bit of like thermodynamics and geochemistry, well, there's some parameters that are regulating when you can have the hydrate as a solid phase and when you cannot. So not sure how familiar you are with guys' phase diagrams, but quickly explaining, on the y-axis we have pressure increasing to the top, and here we have temperature increasing to the right. And then we have this solid line here, that it's actually the line that it's telling us at which pressure and temperature conditions gas hydrates can exist. So anything towards the left of this line, it's stable conditions. Everything to the right, it's not. And specifically over the solid line, we have the conditions of pressure and temperature at which we can have the three phases coexisting at the same time. For instance, in pores, we will have the gas hydrate, which is the solid ice crystalline phase. We'll have the gas, and we also have the water saturated in methane. And if we go a bit more into detail, it's very related to what we call solubility. So I guess you guys had a coffee this morning, and maybe some of you pour some sugar on it. When you're pouring sugar into your coffee, you're dissolving your coffee. And this is what we kind of like relate to solubility. So you're putting something in one phase that it's incorporated into another phase, up to a point where if you keep pouring sugar, the sugar is just going to pile up. You're going to see, like, the end of it crystallizing outside the coffee. This is oversaturation. This is when gas will be exsoluted from the dissolved phase and it will come a gas. So here, it's very important to know that when hydrates are forming, actually your water is saturated in methane just as your coffee might be saturated in sugar. But then we have different processes that can happen. These processes are either deformation, going towards stable conditions, or dissociation or the stabilization of methane hydrates. And here, to have formation, of course, we need to have enough water and methane. This is not something very complicated because when you are in marine sediments, well, water is by default there because we are under the water, but it can also happen in permafrost areas where we have some water, in the areas that have been towing or just like percolating water in the sediments. And we need to have enough methane to have saturation in the system. But this, again, we have microbes almost everywhere on Earth because they are very resilient to the conditions they have. And usually we have a lot of organic matter that they can use to consume and generate this methane. So the first prerequisite to form methane hydrates, it's mostly happening everywhere in the world. The second one, it's a bit more particular. We need moderate to high pressure, as we see here on the y-axis, and also low temperature, or a combination of both might work too. So for instance, if you are in permafrost conditions, low temperature will be dominating, while in sediments, in marine environments, the water column depth or the ice you have on top or of a certain sedimentary basin will be the main factor for the stability of these hydrates. If we are in this term here where formation has happened, we already have the hydrate as a solid phase, but by any reasons, and we will explore those just in a second, we have the conditions changing towards the instability part of the phase diagram. What we are going to have is that these gas molecules that were trapped into the solid structure of hydrates will try to exsolve because the pressure is being released. I guess everyone has had a Coke or a Fanta at some point in their life. You don't see any bubbles when it's closed. This is overpressure. The gas is completely dissolved into the liquid phase. Then you open it, you generate a gradient of pressures. The gas tries to go to the atmospheric pressure. There's a next solution because at atmospheric pressure, Coca-Cola is not longer saturated. It's oversaturated, so the gas tries to get out of the water or the hydrate structure and tries to go to the gas phase. And that's what happened when we call this destabilization, which can be dissolution or dissociation of hydrates. And for this, we need to come back to this side of the diagram, therefore either increasing temperature or decreasing the pressure of the system. And if we look at some, like realistic cases scenarios in which this can happen, and this is why we linked hydrates to climate science, it's because one of the things that can happen is that we increase temperature. But if we look at how the tendency of the water temperature in the ocean is going at the moment, what we see is that both work on the same direction. So the bottom of the ocean and the sea, as well as like the surface of the permafrost, is increasing. And this is clearly one of the factors that can explain the dissociation or destabilization of hydrates. Therefore, if we come back to this cross-section that I put at the beginning, and we look at how we have the water column here, the sediment here, and then we have this solid line here in red, which is the pressure and temperature conditions at which, from here there, hydrate can exist. And then we cross this with the temperature profile in the water column and the sediment. We see that there is an area here that it's, the combination between these two curves at which hydrates can actually exist. So they could actually exist within the water column, but also in the sediment. However, if we have a look at what we just said here, an increase in temperature in the system, actually our temperature curve is going to be displaced. So what before was around 2 degrees at the water sediment interface now might be around 4, which is quite an increase, but just for you to understand. This will leave us with a stability zone that is much more narrower. And that means that any hydrates that were before in this dashed line at the moment will no longer be stable. Therefore, they're going to generate gas. This gas can be accumulated at the bottom, generating what we call a BSR, or bottom simulated reflector, or it can just be escaping at the very bottom part of the sediment. And of course, that will generate a flux that will go into the water column that we will see if it's in the form of methane or something else. Something more that we can explore, and maybe more related to what we were looking at when we went together with the ICM and IGME to Antarctica, is what happens when you release some pressure from the sediment. So we know that if we have some ice on top of the sediment, this is kind of like a pressure as if you had a water column. Densities, ice and water are very similar, so you could more or less estimate if gas hydrates will be stable according to how much ice you have on top of it. But then one thing that can happen is that we decrease this pressure, for instance, by retreating this ice mass. So here we are, from all this water or ice column, we are retrograding this ice shelf, and actually what we have, it's not only a decrease in the pressure that these sediments are experiencing, but we also have some isostatic rebound. So it's like if you're like holding your backpack with 10 books on it, and then suddenly you put it down, you kind of relax your shoulders, right? So this is exactly what the lithosphere is going to do if you remove some ice from the top. It's going to kind of relax and rebound a bit. And when you rebound, you go higher into the topography, and therefore the water column you have on top, it's even less. So actually here we have two processes that are doing exactly what we are showing in this diagram, that it's reducing the pressure that we have into our system. Therefore probably triggering not only fractures, that will be really interesting when we talk about fluid flow, but also a potential dissociation of the sediments. So again, we'll look at what we have. And then from these stable conditions, if we reduce the pressure, now what's going to move, it's our stability curve. So here we move the stability curve to the left, and again, we see that here we generate some unstable conditions. They're slightly different from the first one, because as you remember, the first one can also give you some instability at the top, while here you will only expect the gas to accumulate at the base of the gas hydrate stability zone. But yet, this will also give you some potential dissociation or efflux to the water column, which might look something like that. So you have a bubbling, a seeping system just at the very interface between sediment and water. But then, of course, like we don't want to worry too much about this methane coming out. Is it going to the atmosphere anyway? When you talk about climate change, what people care about is atmosphere, unfortunately, because most of the climate change happens in the ocean. But then, of course, you look at the literature and you see that this benthic sink of methane, it's kind of like the savior of the day. So if anything happens into the sediment, there's going to be a way somehow the organisms are going to be able to catch on this methane that is coming up and use it for their benefit. Actually, what we have here is what we call the sink, which is the very 30 centimeters, 1 meter of the sediment, in which there's a lot of things happening. The first one and most important one when we call about this sink, it's the anaerobic oxidation of methane. So methane being oxidized anaerobically by this consortia of microbes. And this is the formulation that we can see here. So we have the methane that it's in aqueous phase. It's not always the case, we'll see that. And then you utilize some of the terminal electron acceptors that are on the sediment. For instance, sulfate is one of the most common ones because it's very abundant in marine sediments. And then this is transformed into other forms of carbons like bicarbonate and sulfide. We can also have this consortia using the oxygen that it's not only in the water column but also at the interface, in which the methane is transformed directly into CO2. And of course, and we also saw that in some of the samples that we were analyzing in the bottom of the sediments in Antarctica, we can have a lot of bioturbation and bioirrigation, that is any kind of like biological structure that is allowing some vertical exchange between the water column and the sediment that are actually favoring this exchange to happen because they're putting in contact things that are in the sediment with things that are in the water column. And actually, if you look at the literature, what they say is that, at a global scale, the AOM consumes about mostly everything that is being produced in a cumulatively way by methanogens in the sediment. The thing is that we know that there are much more reservoirs of methane than they don't come from methanogenesis. Maybe methanogenesis being accumulated over geological history might be also stored in reservoirs like methane hydrates. And actually, in diffusive dominated systems, so for people who are not into fluid dynamics, diffusion will be the transfer of, for instance, methane in that case, because of a gradient of masses. So I have 2 kilos here, 1 kilo there. In order to have an equilibrium, part of this mass is going to go to where there's less mass. And this diffusive dominated system seems to be quite well, mitigated by this benthic filter. But what we see is that most of the methane that is coming out in the seeping areas is coming out in the form of advective fluid. So where a pressure is actually guiding your fluid to go out. And the velocities at which these two processes are happening are very different and very important in this context. And then if we scratch a bit more like the most modern literature, we see that actually the efficiency of this, a benthic biofilter can be reduced up to 20% when actually the way in which this methane is moving is advective instead of diffusing, and up to less than 10% if actually these bacterial and microorganisms are not present there. So for instance, if you go to a buffet and you have like 2 kilos of pasta to eat on your own, maybe you're not going to be able to eat it. But if you bring some friends, you need to wait until they come to the buffet to eat it. So if there is no one there, who's going to eat all that's available there? So that's also something that can happen if we do not have a community that is ready to eat all the methane. They might not be able to do it. And actually, if we look at even like the most recent papers, there's not a lot of literature on that, but some things are coming up because we see that this is happening more and more in the ocean and also in the permafrost. We see that actually, if you look at Antarctica and the Southern Ocean, they see that they needed to wait up to 5 years to see that the community of microbes was big enough and efficient enough, because you can have microbes and bacteria that are not specialized are eating methane. So it took up to 5 years for this sediment to become a filter of all the methane that was coming out. And I don't know about you, but in human scales, 5 years sounds like a lot of methane that could have been escaping from these systems. If we look at some modeling efforts that are less refined of what we are doing, we are trying to build something that is fully coupled, that links all the processes that are happening in the system, which is complex. That's why no one has done it yet. We see that the AOM actually it's pretty inefficient when we have some permeable pads. If you have fractures, microbes, even if they're there, like this is like comparing, I don't know, the diagonal of Barcelona with like a tiny street in the Raval. In the Raval, you might be able to see the people passing by, everyone is going pretty slow, chill. So if I'm a bacteria there, I might take some methane, walking next to me. But if I go to the diagonal, like things are going so quick, diagonal will be like a fracture, in the system, and I'm not able to catch up on this methane, even if I'm a very, very efficient bacteria. And finally, of course, here we could put on top what we saw on the Ice Flame project, but I don't want to spoil anything until it's been out. So there are other studies that are seeing that actually it seems like we reached a tipping point. Like in the Arctic, we have about 17,000 active seeping areas where methane is seeping. In Antarctica, more and more and more, we see this is like a growing pattern. So there is methane being seeping in very specific places where actually methane it's not so deep, it's quite shallow and could even go to the atmosphere. So that opens a bit of okay, what's happening? This is not as efficient. And it makes us question which are the ways in which this methane can come up. So one of the things that we need to take into account is how are things moving? How is the flow, including liquid and gas, are moving into the sediment? Here we will have again this cross-section in which we see the profile of sulfate coming out from the salty water into the sediment and the methane. And this, where one is ending and the other is starting, it's called the sulfate-methane transition zone. So you do a transition between sulfate-dominated to methane-dominated areas. And usually in places where there's no seeping, that happens, below the interface. What we see is that if you are not in a diffusive flux-dominated system, but in a system where things are moving at a much quicker rate, then actually this methane profile is being pushed up. So it's not the same to wait for, something to equilibrate. Like imagine you have a bucket of water and you drop, a tint. You will see this diffusion into the water of the particles. But it's not the same to do this than throw something with a lot of energy into the water. It will move much quicker. So these two velocities at which things can happen can actually explain this methane being closer to the sediment, pushing even the sulfate upwards and being able to go out into the sediment interface. So we are moving the whole system vertically, and this is actually creating, first of all, a stepping on solute gradients. So if you don't have methane into the water column and you are pushing methane up, it's not only advection, you are also generating some diffusion at the very top of the sediment column. And also, if I'm moving the whole system up, if I had a very efficient community here, perhaps in a few days or months, if my sulfate methane transition zone is being displaced centimeters away into the sediment column, these microbes might not have moved upwards. They cannot climb into the sediment unless they are being pushed by the flow that it can happen. They can be transported by bubbles, but it's not very common. So you start from scratch at eating this methane. So that can debilitate the efficiency. And then if you put hydrates into the system, then hydrates are supplying a lot of methane and also supplying the methane mostly in the form of gas, because for them to be stable, conditions of saturation needs to occur. So if you are generating some more methane, this methane will go directly into the gas phase. So here we are not only increasing this advection in the form of dissolved methane, but also in the form of gas. And we might probably also create some fractures or use some permeable ways that are already existent reopen fractures in the sediment using faults in order for this gas who's under pressure to get out into the system. So here we actually have, the first thing is that like this consortia cannot access gas. So if you look at the very like biogeochemical way in which this community of microbes and bacteria will use this methane, they need to transform the methane into the form of gas into dissolve, and then they can use it. That means that the speed at which these microbes needs to eat the methane needs to be quicker than the velocity at which the gas is moving, because they need to redissolve the methane in order to have it. But if the methane is, like moving upwards quicker than they can dissolve it, then they cannot access it. So this is the first one. Then if we have fractures again, if this fluid is going too quick, microbes are efficient, but like they're not machines, so they can't actually reach this methane, and it bypasses completely the sink. So here we not only have some physical processes that are like hindering how much these microbes can eat, then the consortia itself, it has some limitations, because this is, for people who are not into biogeochemistry, someone will present the AOM, or anaerobic oxidation of methane, with this formula. But then for someone who works on the real formulation of how this happens, there's a few more terms. First, stoichiometry is important, but also we have a B here, which is actually taking into account how much or how many microbes do I have into my consortia. So here, the more they grow with time, the more I'm going to be able to consume. Again, if you have a lot of pasta, you will eat it quicker if you have a lot of friends who are into pasta as well. So here the rate, it's actually controlled by how many of these cells are present into the sediment in order to eat. And this, it's not something simple to modulate and to understand. There's like some kinetic factors, there's some thermodynamic factors, and there's some bioenergetic factors. So these microbes need to grow, but they also need to meet their energy requirements, and they also need to be in, they need to agree with how the geochemistry of the environment is at that moment. So if I don't have enough sulfate, I might not reach my kinetic limitations, and I'm not going to be able to eat at the speed that I'm supposed to be eating this methane. And if we have a look at like a few graphs here, this is a preliminary simulation of how much and how quick this methane is being eaten, so the rate of this anaerobic oxidation in time. And we see that at the beginning it's actually pretty low, and it's only at a certain moment around in this simulation of 50 years, it's when we do have the fluxes going pretty high. And this peak, it's actually understand because the biomass, it takes up to 50 years for this simulation to have enough cells of this consortia to eat the methane. So up to 50 years, my flux of methane into the water column is going to increase exponentially, and my rate of eating this methane, it's not going to kick in until that moment. That means that, for instance, here we will be talking of what we call a window of opportunity of about 50 years. These windows can change according to how do you model this, how much flux of methane you have, how much consortia do you consider you have initially into the system, etc., etc. But it can go from days to hundreds of years. So this is a big unknown into our community to know actually from whatever is being dissociated from hydrates, how much could actually reach the water column. And that's not the only implication, because we might not know how much is going to go out, but in which form this is going to go out. Because if these bacteria and this consortia is eating part of it, they are also modifying where this carbon is going within the different carbon pools that we have into the sediment. So for instance, here we can have direct emissions of methane in the form of dissolved methane and gas, but we could also have, for instance, some CO2. If I have some methane that is being ejected, in the way it can be oxidized, but if it's in the water column, it might also become CO2, meaning that we might acidify the water locally. And then Also, we can, and this is what we try to measure from the water samples, we might also change the dissolving organic carbon of the system because we are generating all the time with the anaerobic oxidation some bicarbonate, and also the total alkalinity of the system because we have bicarbonate and sulfite being as an input from this consumption of methane. So actually, whether we are producing DIC that can acidify the local waters or alkalinity, which has a buffering effect, all of these, it's not only regulated by AOM, it also needs to go together with what's happening with the byproducts of these reactions, of course, but it does change the carbon cycling in the sediment and the water column. And we do know that the climate it's regulated by the composition of the ocean. So if we do change the composition, if we acidify the ocean, even if it's locally, we might have less buffering effect from the ocean to absorb CO2 from the atmosphere. So this is important not only because the methane can get out as methane, but if it does not get out as methane, and actually this benthic sink, it's efficient, it might drive some other changes into the carbon cycle that are also climate related. And to do that, you need to model somehow because the data we have is very limited, and also because one of the ways to understand better a system is to try to model it and put into equations what we think we know about it. And that's why I have created, this is the workflow of the model, and at the very top what we can have, it's, you know, obviously you start, this is the mathematical solution, just there in case someone is curious, but I guess no one will look at this. But if we look at the processes, we need to, first of all, know how much methane is in the system, how much is into the hydrate phase, how is this hydrate being stable or not? So here we will have the climate drivers destabilizing these hydrates or climate forcings. Then we need to know how much hydrate has been delivered into the system, or this can be actually measured into the field as well. And then we have the benthic biofilter, which can in a way be bypassed because we have seen that if it's in the form of gas might not be filtered by these microbes, or if there are some fractures, it might not be filtered as well. So we have a fraction that it's not passing, so it's bypassing the benthic filter. And then if it does bypass, then it will go into possibly directly the water column where it can still be oxidized with oxygen, or it will just have a direct benthic environmental impact into the water column. If it does, then we need to look at like how these microbial dynamics are happening, all the limitations I told you about, whether the gas is in the gas or the aqueous phase, if there's oxygen in the sediment, and so on and so on. And at the very end of it, what we want to understand in order to have a relationship with like potential climate feedbacks, it's how much we can inform Earth system models or ocean models. Because when we do climate predictions, we have the atmospheric box, and then we have the ocean box, and these two, they're quite well connected. But the bottom boundaries of these of these ocean boxes, they're quite not well understood, and there might be a lot of carbon in different forms that we are misunderstanding in these systems, and that will actually connect to the capacity of the ocean to buffer climate change. So just as a take-home messages, every message is in the same color. It's supposed to be in the same color as the plot. But understanding the production or release of methane from the stabilization of gas hydrate, it's important. It's important not only because we have a global methane budget that we need to understand better, because we know the climate predictions we have a lot of uncertainty, and it's better to be on the safe side of the equation, but also because we have a lot of feedback that can be connected to this climate. So if methane or other forms of carbon are being ejected into the water column, that might affect the predictions that we think are kind of like something we can rely on. Also, we need to better understand what's happening with the AOM, because it can be efficient, but at the same time, it has biogeochemical impacts on the benthic area and the water column. And this is just not climate related, it's also ecology related. If you are acidifying certain places where seeping is happening, you might have coral bleaching, you might have some species that can no longer live there, you might have a competition for the terminal electron acceptors that are on the water column. So it's important at many biogeochemical levels. And finally, and because I'm into a bit of like politics, you know, it's important to understand if there's some projections that can be, you know, done in terms of the regulations. If we know that the permafrost, it's going through the same kind of like feedbacks, we need to put more stress into stop emitting and melting areas and having climate drivers that are emitting even more methane than what we are emitting as a human species. Because actually we have environmental feedbacks that we do not know very well and that might trigger some other tipping points or cascading effects that we need to better understand. So it is important, yes. Do we have a lot of data? No, that's why we went to Antarctica with some of the people in the room. And modeling, even though it looks a bit, you know, difficult for some people, it's a very good tool in order to start understanding where we need to look at in order to solve this piece of the puzzle. And with this, I'm just going to leave you with my website, which is still under construction, but I try to do as much communication as possible about methane. And thank you for your attention.
Hola. I don't know why you're laughing when I want to tell you something.
Just in case.
Anyway, thank you for your talk. It was very interesting, and I think it reaches very well geology and biology, which is something we do not often do very well. Myself, speaking as a geologist, I just tend to look at one side of what you explain, and I think for biologists, it's on the other side. But your talk was quite in between, so that was good. Just to try to understand the rates at which those things happen, you've been sort of showing trends in water, in surface water temperature, and how this could affect methane hydrates. You've been putting some let's say thermodynamic plots with your talk. But I mean, how those surface temperature changes affect deep water temperature changes, which is what will have an impact on the hydrates, and how those bottom water temperatures will propagate at the depths at which methane hydrates. And that's just for you to explain us a bit about the rates of at which hydrate dissociation might occur.
Yeah, so this is a very good question, especially when you do modeling, because one of the big challenges in this modeling work is to put within the same time step processes that are happening at very different geological scales. So Roger is right, hydrate thermodynamics, they move at very low rates. Let's say we can have changes from centuries to millennia when it comes to destabilizing hydrates, and then depending how deep they are on the sediment, we have let's say the sediment can transmit temperature at a certain rate, which is quite slow, and then you will have a lot of years, decades to centuries, to perhaps reach 100 meters where these hydrates might be, and then you have the thermodynamics that are happening quite quick, but then you also have hydrates being a phase that can self-stabilize. So for instance, the dissociation is a very quick process after a very long centennial, perhaps climate forcing. Then dissociation happens really quickly, but then self-stabilization happens really quickly. So maybe the output of these methane emissions can only be read in, again, terms of centennial timescales. While the work of this microbial consortia, it's of the rate of millimoles per day. So this is something that is happening super quick. So here, the main issue is like when these hydrates are already dissociating. So of course we cannot say that what we see right now in the bottom of the ocean as an increase of temperature in the next years will be a trigger for methane emissions within the next 100 years, but we know that changes have happened in the geological history. For instance, in Antarctica, temperature is a bit more delicate, at least for marine sediments. It will take much longer for this methane to get out, but for permafrost, surface temperature relates directly within days, weeks, or months into hydrate stabilization. So it also depends on the environment in which you are working on. But for instance, if we talk about depressurization, which is also like depressurization would be like you remove like the ice, for instance, and the pressure from the sediment to very deep in depth. If the water column within the sediment, so the pores are well connected, might be something almost instantaneous. The rebound will be something that takes more time because it depends on the elasticity of the sediments that is trying to be relaxed. So the scale will be depending on the environment, will be depending on the climate forcing. But what's very interesting of the question is that microbial rates and hydrate thermodynamics and climate forcings, they work at very, very different scales. And you can only look at the work of microbes when the hydrate already it's supplying methane into the system. But the whole trigger to thermodynamic instability and migration of this methane within the water column to the benthic environment, this is such a much slower process that usually falls within centuries to decades, if not geological scales of millions of years for ice stabilization of the lithosphere. So it will be very case dependent specifically.
First of all, thanks for such a good talk. I want to ask again, what are the factors which leads to the release or dissociation of the methane gas from the gas hydrates?
Yeah. So hydrates are stable solid phases, right? It's like ice. For ice, you only have one boundary, that is temperature. Below 0 degrees, unless we're talking of capillarity, you will have the ice being frozen and solid, and above 0, you will have the melting. Here, if you see, we have a stability curve that it's actually not linear. This is ice. Above 0, you have melt ice. Below, you have a frozen. This line converts into this parabolic line when the gas is considered within the structure, right? So here, because of the shape, you have two variables that are controlling the stability. One that it's pressure and the other one that it's temperature. So factors that are controlling the stability and therefore might trigger dissociation or destabilization would be either a decrease in pressure, either an increase in temperature, or a combination of both. And how you can get to those, it would depend again into the environment. So if you have ice being melted on top of a sedimentary basin, like it happens in Antarctica, then you are releasing some pressure. If you have an input of warmer water in the base of the ice shelf, you're increasing temperature. If you have permafrost with melting glaciers and thawing of the sediment, you will have both at the same time. So pressure and temperature variations that makes you get out of the system will trigger, but how do they happen and which is the factor that is controlling the most will depend on the environment that you are looking at.
Is there any other factor than the pressure and temperature?
Yes.
Or just
So because we are talking about crystalline compounds, therefore there's like bonding in between the molecules and so on, one of the things that is very important here is the activity of the water. So anything that is dissolved into your water might have an effect on how strong the links in between the water molecules are. And therefore, for instance, if we see this dashed line here, this will be the same stability line, but adding the salinity of the ocean, which is about 35% parts per million. And then this means it's the same as if you have, like, if you go to the Pyrenees and they want to go with the truck, they don't go and put like a flame on top of the road, they throw some salt, right? So it's the same active factor. You modify the activity of your water, including some chemical inhibitors for the stability of the water structure, and then you can also destabilize. So for instance, in polar regions, you have always fresh water in the ice form. But then if you have a melting, if you have some intrusion of marine saline water, you are not only introducing warmer water, for instance, in the base of an ice sheet, but also saline water, which does not allow the hydrate to be stable. So you would be stabilizing also because of this. But then again, as hydrates, the dissociation is exothermic, so it will, it's endothermic, it will cool down the environment, so it will reform as soon as possible. The fact that you are liberating fresh water, because when you melt, this is only fresh water. Salty water cannot be a crystalline component unless it's in the form of imperfections inside. Then you release some fresh water, so you kind of like recover this, at a pore scale. So they try to stabilize very quickly. It needs to be something very vast in terms of the magnitude that will allow you to have a bursting of methane from these systems.
Thank you.
Hi, Maria. Thanks for the interesting talk. It was very didactic, so very nice for us. I was wondering what kind of microbial dynamic data you use as an input for your models.
We're hoping to have some from Anna at some point. At the moment, what we have, mostly in UCLA and USC, they have some data on incubations. So what has been done until now, also because in Santa Barbara Basin, there's like a lot of methane coming out, so it's a place where they go, they collect some cores, and they put them on the lab. They kind of like, at the moment when they're collected, they don't have any methane circulating in the system. And then what they do is they inject some methane from the bottom, but we are talking about less than 20 centimeter cores, so the representativity of it's limited. You inject some methane on the bottom, and then you see how much methane you capture at the very top of the sediment. So you calculate a flux, and everything that is not coming out in the form of methane, it might have been eaten by these microbes, so you can calculate a rate. When you do this, you see that as soon as the microbes are they found some methane into the system, they will eat it. But this is not realistic, because you might have had a community that has been fed by methane for, I don't know, like centuries, because you have a sipping going on, then it's stopping, then you have another burst, or you have a lot of methanogenesis happening because you have sedimentation rates that can be really big at certain moments in times, and then you have a lot of organic carbon being buried, a lot of generation of methane, and then they get used to this amount of methane, and then they don't die that easily, right? Because instead of growing, they prefer to self-preserve themselves. So you can have a big community that has been inactive. The energy limitations for their survival are very low, so they can stay into the sediment for centuries without changes in their community number. So the data we play with is the rates that are taken from either sediment cores that have been injected, like experimentally on the lab, or by people who goes there, they see, and now I'm talking against, what other people before me has done, which I don't like, but it is the reason why we're doing this. I don't know if it's, yeah. So people go to the field, they measure this, because this is something you can measure, right? You take your sediment, you use a Ryzen for the pores, you take the chemistry out, and then you see these two lines, and then you take a very simplistic model, which exists, and then you calculate how much methane you might have had during the system, and you kind of like back on the envelope calculate how much methane they might have been consuming. So the rates for these are huge, because in order for methane not to get out, you might have had a huge AOM rate. But what you see is that if you go to nature, that it's not what we see. So we have estimates of these velocities, but how relatable to what you might have in bursting environments that are climate forced, that's an open question. That's why we want to see what's going on in Antarctica, which is quite pristine in that sense, and also to, feed these models in a way that what we get, it's answers more than just solutions from the model, right? If the more you constrain the other parameters, the more you can narrow down to your question of how much they are eating, or you can have at least, a range of values that would make sense. But for this, we need, of course, data that it's being collected at the moment. What's been more studied, we have a PhD student in Germany studying the methanogenesis, because, for instance, in the permafrost, it's more important to know how much is being generated now than what can be escaping from pre-existing structures. So we have very, very, very limited data. That's why we want to do models that we understand very well and that very well mathematically constrain, so that we can reduce the uncertainty to only the rates of AOM oxidation.
Hello, thank you for the talk. I was curious about just that you just mentioned about methanogenesis, because, during the talk you were talking about how the methane was released from the sediment, but how that will affect the production, the new production of methane in Antarctica sediments or stuff like that. So will that be balanced somehow over a given geological time?
They're disconnected processes. So hydrates are a relict of the methanogenesis that happened, or thermogenesis if the molecule was break down at a very deep environments. So methane can be generated either biologically. You have a methanogen that eats the carbon from organic matter and generates methane as a byproduct. Or it can be generated when the organic matter is buried too deep by thermal breakdown of the molecule, can also generate methane. So hydrates are a proof that methanogenesis had happened for a very long time, and they're accumulating this methane. This is one reservoir. If hydrates dissociate, this methane is going to be accumulative to whatever it's being generated at the moment within the sediment column. And this methanogenesis will depend on the sedimentation rate. So how quickly is this buried? Do they have access to it? It will depend on the quality of the organic matter, because liable carbon might not be as reactive depending on the quality of it, if it's been transported for too long, if it has been exposed to oxygen for too long, if the surface of the carbon particle is too big or not, how much methanogens do you have there, what's the chemistry, is there anyone else competing for this liable carbon? It can be oxidized into the rusty, the rusty carbon pool. So methanogenesis happening at the very first meter of the sediment, it's something that's completely disconnected from those, but in a way that they interact is when you are at the very top, if there's a lot of methanogenesis happening, then you have quite of a highly saturated system when it comes to dissolved methane. And then if you have hydrates dissociating stuff, and the gas is being reaccommodated into the dissolved phase, then you might force some X solution at the top, because methanogenesis is generating a lot. There's more being introduced, so methane actually reaches oversaturation at the very shallow depths into the system. So it might play a role into potential exchange with the atmosphere because of oversaturation if methanogenesis rates are very high. But as process of where the methane comes from, they're completely different. They're geologically distant, right? Hydrates are very old reservoirs of this methane. And for instance, if the conditions are good at the very top for hydrates to exist, maybe some of the methanogenesis that is happening can be already stored in hydrates. So they play a role together, but they're two different sources of methane when it comes to how do you model them. Does that answer your question?
Yeah, sure, but that create a new one.
Okay.
So then, if temperature or pressure is, if temperature is going higher at the bottom,
Yeah.
or pressure is going lower, how that will affect in the surface layer the new methane production?
If it's only methanogenesis,
Yeah.
that will need to have a relationship with the thermodynamic and kinetic constraints of the methanogens. So for instance, we know that the more temperature you have, the more active they might be. So you can have some thermodynamic processes within at a cellular level of this consortia that might increase the rate of consumption of organic matter, therefore more production. But this is something that we are exploring at the moment, because what we know about microbes is that we don't know anything, right? We know that they can grow, we know that they can die, we know that they can be completely like, kind of like frozen state and then reactivate super quick, but we don't really know. We know that temperature might have an impact, because in the Arctic, the warmer it is, the more methane they generate. That's for sure. So there's like a linear, or at least for a certain period of time, there's a linear relationship between production and microbial activity and temperature. But for these systems, we don't really know. But it might be that both, temperature increase will push methane to be ejected, in both cases. First, because you might destabilize, and second, because you might have more methanogenesis. But again, if your liable carbon it's not good quality, or the sedimentation rate it's too quick, they might not access the carbon. So there are other diagenetic limitations that are in place for the generation of methane through microbial activity.
And oxygen conditions, right?
You can have both, huh? So you can have, and one thing is methanogenesis, and another thing is methanotrophs. So the ones eating, they can do it both in anoxic or anoxic conditions. We know that it's much more efficient in anoxic conditions, because when you have oxic conditions, oxygen is so important for so many biogeochemical reactions. There's a lot of competition for it. So usually, methane oxidation, if you look at the redox ladder, I don't know if you're familiar with it, might be one of the, if not the last one, to be taken into account. So there's like a priority on how the reactions are going to happen, and that will be the last one when it comes to using oxygen. So if you have anoxic conditions, might be much more powerful, at least for oxidation.
Thank you.
Any other questions?
Okay. Well, thank you so much. I'm just going to leave the last one.